To talk about rate expression or rate law, I'm looking at Haber process, which is nitrogen plus hydrogen giving you ammonia. And if you note, this time I put Fe solid as reactant and it's being produced as a product. Therefore, Fe is a catalyst. It could affect the rate of reaction. You usually do experiments to see if that's true or not. So if I write rate, it could be definition of a change in concentration of reactants per unit time. Instead of delta, the triangle, I put d, which is a smaller change over change of temperature, dt. So this is also equal to minus change of concentration of nitrogen over change of time, which is equal to change of concentration of hydrogen over time. And we put the factor of 3 in the denominator because as you use up nitrogen, hydrogen gets consumed 3 times as fast. Now this time the rate expression has a constant K in front of concentration of the reactants, Fe, to a power known as order of reaction X, multiplied by concentration of nitrogen raised to a power of Y, multiplied by concentration of hydrogen raised to a power Z. So the few terminologies we should get exposed to. First is the K, rate constant. It is a proportionality constant, or you define it as constant of proportionality. It describes how the concentrations of reactant are affecting your rate, so it's that. And you can only find it experimentally, and it's function of temperature. So K changes as you change temperature, so it's proportional to temperature. At a given temperature, K is constant. Now, eventually, in a couple of slides, we are going to get into details of this, but there is an Arrhenius equation, which K is proportional or equal to another constant A times E raised to power EA over RT. Now, A also has a name. It's known as Arrhenius or frequency constant. Which quantifies your steric factor or geometry, how particles should collide in proper geometry. EA is activation energy, minimum energy you need for a reaction to proceed. It's constant for a given reaction, nothing changes that. Temperature should be Kelvin. And R is your gas constant, which is 8.314 joules per mole per Kelvin. So that's what K is. Now X, Y, and Z are known as order of reactions. So X is order of reaction with respect to A. It is exponent. So if they ask you to define it, it's simply exponent. It's mathematical term. Exponent or power by which the reactant A changes concentration. Exponent by which A or concentration of A changes or affect the rate. Now one thing you should notice that X, Y, and Z are not your coefficient necessarily. They have nothing to do with stoichiometry. We have to find them experimentally again. When you add X and Y and Z, that's known as overall order of reaction. You get 1 point by being able to say what's overall reaction for something. Now what you should know that K and order of reactions are again You can find them through experiments. So they have nothing to do with your stoichiometry. In the next slide, I'm going to do one calculation where we are going to calculate order of reactions and the rate constant K.